joke is going around.
Okay, folks, we have a possible final project here that Alex would like to explain for a couple of minutes.
Yeah. Cool, thanks. How many of you guys actually know what you guys want to do for your final project already? Like 100% for sure. Can you guys raise your hand?
All right.
Cool, it's a small number of you. So when I first heard of ECE 4760 and I looked at some of the projects from before, I was like, wow, these are really cool. But then when I got to looking at them even closer, I noticed that not many of them really give back to Cornell. Not really, they don't really truly benefit. They're cool startup projects, but they don't really have an impact yet. And then also very few of them carry the interest of President Scorn himself. And that's something that I'm here to propose today. So I'm working on a project to really change the way people see environmental waste. And it's called Project Green Stations. So what we're trying to do is, with a team of one of the best designers on campus, we're trying to change the way people see trash and waste. So if you look at the trash cans we have right now outside, the normal trash and recycling, that's from the 20th century. That's all old stuff. It's junk. It's crap. What we want to build is something in the 21st century. We want to build the next innovative, sleek design, sleek looking thing that can really fit in with our 21st century technology. And we want to build a better trash can, basically. As simple as that sounds, it's really complicated. And our best design teams are completely confused as what to do already. But what we want to do is not only have a good design, we want to have smart components. We want it measuring how much waste there is, how much volume, how much capacity, and upload that data online in next to real time, maybe every hour, every half hour or so that the waste management team can see that data and know exactly when to empty the trash cans. But not just that, have that information open sourced so that people who are interested in this type of stuff can go calculate, oh hey, if we modify the routes so that this person A goes to route 1, 2, and 3 and then does 6 and 7 later, it's more efficient than the current system we have now. We want to make a better technology. We want to make things a whole lot cooler and a lot more innovative. And that's what Green Station is about. We want to make a better trash can, and we need your help. So Professor Lan has generously offered to use maybe 1 or 2 teams for their final project to work on Project Green Station in collaboration with my design team and another group that we have going on. And I think that would be a really great opportunity for all of you guys to give back to Cornell and also to really make a difference, because that's what it's about. Thank you.
Thanks. So as an external research program, we would, of course, waive the budget requirements if you were to be interested in this. So write a net ID on the board.
I made it big for you guys so you guys can see. AWC65. If you guys have any interest, shoot me an email. I'd love to hear your opinions or thoughts. And if you'd like to work this as your final project, this would be really awesome.
All right, thanks.
Thanks for your time, guys.
Thanks. Smart trash. I like it. Some really interesting sensor problems here, because whatever the sensor is that you put in one of these cans has got to be amazingly robust against all kinds of assaults, mechanical, wham, slam, chemical, blah, blah, in goes the lemonade. It's really, lemonade's pretty corrosive, but not as bad as Coca-Cola. And so there's lots of interesting mechanical and electrical problems here. On a different note, I changed the consulting schedule online. You're going to want to look at that fairly often. We're going to be open Wednesday 10 to 12. In the morning, yes. Thank you. Consulting hours are always in military time. If it had been, that would have been 2200 to 2400. For just exactly that reason, I've had people say, "You meant 7 in the morning?" Right. So, open Wednesday 10 to 12. We're going to open Thursday as soon as I'm done with lunch. That's usually noon, sometimes 12:30, but certainly earlier than 1:30. Probably no later than 12:30. And there is no Sunday hours this week. There probably will be next week. There's sort of a natural cycle here where people need a little extra time every 2 weeks. And we're deeming it a better use of the grader's time as a consultant to be in lab Wednesday night when the place is packed and steaming. So that's the schedule for this week. I modified lab 1 slightly to make it easier. Sorry, lab 2. Lab 2. Lab 1 I'm not going to make easier now. And the way I modified it was to specify you don't have to use the keypad. You can just use the STK500 buttons. There's no strong use for the keypad here. I was thinking about bringing it in so that lab 3 would be easier. If you want to get started on lab 3, you can bring in the keypad. If you feel like you're stressed for time in lab 2, leave the keypad integration for lab 3. Any questions about lab 1 write-up or anything about lab 1? Questions about lab 2 so far? It's not too late to start, folks. Lab was not full yesterday. I'm going to draw the schematic up here again and talk about it a little bit more. After a few questions and a few comments that I've gotten, I think I better talk about it some more. So it's going to be some sort of DMM probe. I think is the way I said it on the website. It's going to go through a 1K resistor for current limiting, then to a pair of snubber diodes, one to VCC, one to ground. The combination of the current limiting resistor and the diodes protects the analog inputs. And the reason that we're doing this is that you're probably going to hook up the digital multimeter probe here, the probe to the signal generator, which can output as much as 20 volts and will blow out the whole input section of the microcontroller unless you snub it to 5.6 to minus 0.7 volts. Going to go into the ADC here, and one thing you're going to find, and you should try this, you will find that if you put an oscilloscope probe on the power supply, or in fact any digital output of the microcontroller, that the microcontroller produces a phenomenal amount of analog noise. As much as 150 millivolts on the power lines. Now the circuitry you didn't know you were building, but you're building anyway, the parasitic capacitances from the power supply to this wire will couple that noise into the ADC. And so you'll have a lower accuracy on your measurement because of digital noise from the microcontroller. What do? What could you do? Yeah, you could low pass filter with a capacitor. So you could put a capacitor right here to short out the high frequency noise that makes it through the 1K or is capacitively coupled in here. How big should that be? What size capacitor should that be?
0.1U.
Well, the correct thing to say is, how often are you going to take a measurement? Because you're setting a time constant here, right? Frequency of the noise is broadband up to about half a gigahertz. But the low end is probably on the order of 100 kilohertz. Good question. Because that's the other time constant you need to worry about. So, yeah, what bandwidth do you want here? I really said we're measuring DC voltages, resistances, which don't change very much, and frequency, which you can... Ooh, is this going to bother the frequency measurement? I know what we can do. And so, yeah, you have to choose this a little bit carefully so that it's big enough to short out the noise spikes, but small enough to let through the signal that you're interested in. And so if we're going to measure a maximum frequency of 100 kilohertz, let's see, how many radians per second is that? That's about 600 radians a second, so that's about 1.6 microseconds, right? So how big should the capacitor be? About a nanofarad, right? That's about 10 to the minus 6. Something like that. Maybe a little bigger. Mess with it until you get good signal to noise. Secondly, specified that B.3, let's make this a little more explicit out here. We're going to hook this probe to one of 3 places for testing. If we hook it to the signal generator, then we're going to hook it to the TTL output of the signal generator. TTL output's a separate BNC connector. You have to physically change it on the front of the panel. We're going to hook it to the TTL, and obviously the ground on the TTL goes to ground. The TTL output goes to ground on the microcontroller, and you have to do that by connecting the grounds together because the microcontroller is floating. It has no ground reference relative to Earth. Even with the power supply plugged in. It is an isolated power supply. We did that on purpose. So that's one mode. Second mode is measuring a DC voltage with a trim pot. Now, there are 3 connections to the trim pot, and there are three possible signals you can put on the trim pot: VCC, ground, output. You've got 3 things you can connect to a device with 3 leads. How many possible ways are there to connect it? Six or 9? It's 6 because you have no replacement, right? You can't connect two leads simultaneously. So there's 6 different ways. How many are correct? 2. It is correct to connect VCC here, ground here, and output here. It is correct to connect ground here, VCC here, and output here. It is incorrect to connect the output here, ground here, and VCC here. And why is that? Because you're going to say, I wonder what happens when I go to this end of the trim pot. You drive this down until you hit VCC, you short the power supply, and one of 2 things happens. First of all, you'll probably brown out the CPU. But what may happen before that is that you blow out the trim pot. Because the trim pot is rated at maybe 100 milliwatts, and you're going to put a very large wattage through a very small resistance here, you're going to pop it, and then it never works again. Now, yesterday I saw one trim pot that was almost too hot to touch. That's a bad sign, folks. Also, there's a light on the board. It's called VTG. If VTG is dim or goes out or flickers, it means you have a short circuit. Don't think about it. Turn off the power, disconnect all the wires, and then think about it. I actually burned my finger on a regulator a couple of days ago. So, the moral of the story is, before you do anything with this trim pot, you hook it up, you make sure that one end is at VCC, the other end is at ground, and that when you turn it, hook it to the digital voltmeter, and when you turn it, you should get a smooth change from one voltage to another. You do that before you hook it to the microcontroller. Okay. The third mode then is going to be to connect a resistance to ground, some RT, resistance under test. You're going to turn on one of these resistors, so you're going to have some RS down here, which is connected to VCC, going up here. You're going to have some RS, some RT, so clearly the voltage here then, the voltage here is going to be RT over RT plus RS times VCC. And you're going to get RT, obviously, by solving this equation. You're going to measure the voltage using the ADC. You know RS, and so you know everything to get RT. However, there's two boundary conditions that lower your accuracy, and you have to watch out for. If the voltage here is very small, let's say that RT is small compared to RS. If RT is small, much smaller than RS, then V is going to be small, and ADC noise will dominate the measurement. After all, if we have the ADC set to 5 volts maximum, and we have 256 voltage steps between 0 and 5 volts, then the step size of the voltage is about 0.0039 volts, 3.9 millivolts, call it 4 millivolts. And if you're measuring a voltage here of 8 millivolts, you only have one significant bit. You could be a factor of 2 off. That's not good enough. So very small resistances are going to cause ADC errors. What about very large resistances? Let's say that that RT is much bigger than RS. Now you're going to be in a position where the voltage barely changes at all if you change RT, because it's so close to VCC it can't get any higher. And so you're going to have low sensitivity if RT is much bigger than RS, and low accuracy if RT is much smaller than RS. Doing calculus by guess, we would therefore say, maybe they should be equal, or approximately equal. That suggests that we're going to need several different values of RS, and I think I specified 1K, 10K, and 100K, that you can switch on and off independently, so that the voltage that you measure is always about VCC over 2, plus or minus, at least no smaller than 0.1 VCC and no bigger than 0.9 VCC. So you'd like V then to be, well, let me make this 0.1 VCC is less than, V is less than 0.9 VCC. Any questions? Question? So, the last thing we need to do, the last piece of circuitry which we talked about last time and which I want to expand on a little bit, is the input to the comparator. One side comes to B2, which is this input here, and the other side goes to B.3, which I drew this way before. VCC, 10K, 10K. So we have a one-to-one divider, so this is set to VCC over 2. Right? This makes an assumption. I'm willing to have you use this assumption. This particular circuit makes the assumption that whatever waveform you're putting in here to measure the frequency of has to pass through VCC over 2 on every cycle. So if we set the comparator to VCC over 2, then on every cycle, whatever the waveform is that you're measuring, it has to go through VCC over 2 once per cycle, or this circuit won't work. Because the comparator will either stay in the high state or the low state indefinitely if you don't go through VCC over 2. How could you make this circuit better? I was pointing in line and you both answered. That's simultaneous parallel processing.
You put a low-pass filter such that you get the average value of the wave onto B.3, and
yeah,
then it's going to have to pass through that.
Right. So you could do something like this, that B.3 gets an input which is V in, like this, where actually I don't even think you need this. You have V in and you have some fairly large capacitance where the time constant here has to be much bigger, somewhat bigger anyway, has to be bigger than the frequency of the slowest wave you wish to measure, the lowest frequency you wish to measure. And it has to be smaller than the repetition rate of the measurement. It will be sufficient for this lab if you stick to using the TTL output of the signal generator. If you do that, the wave coming out is guaranteed to be 0 to 5 with a fast transition through VCC over 2, and therefore this will work. Now, this is another significant source of noise we haven't talked about. This being analog, we have to talk about sources of noise always. And that is, you are surrounded at all times in this building and every other building you're in by huge electric fields due to those things. And so the gradient across my body as I'm standing here is about 200 volts from head to toe. And there's a current flow, a constant current flow along the skin of about 100 nanoamps, corresponding to current coupled in capacitively from the lights and coupled out through the concrete floor. So 100 nanoamps, it's not a problem for you. The input impedance of the ADC is rather higher than your input impedance, and it'll notice a small current. It'll build up a fairly large voltage, and you may find that your voltage measurements are dominated by 60 hertz noise if you're not careful about making the circuit. How can you tell? Well, obviously you put an oscilloscope on this wire and see if there's 60 hertz noise there. Hopefully low-pass filter will help, but not if it's a 1 nanofarad capacitor. That's way too small. So what else could you do? Do you know what a commercial digital multimeter does to avoid 60 hertz noise? Battery doesn't help. It's coupled in through capacitance into the leads. Faraday cage, magnetic shielding. Yeah, that's a fairly intrusive, although I have been in environments in neurobiology where all measurements are done in a Faraday cage for exactly this reason, because Faraday showed that if the inverse square law is true, then all energy on a screen, a closed screen, goes around the screen and down, and then there's no field inside. So, what can you do without building a Faraday cage? Real digital multimeters don't come with Faraday cages, although maybe they should. But you put them on and you get no 60 hertz noise. How can this be? Huh? Huh? That's an interesting idea. Could be a notch filler, 60 hertz notch. It turns out it's even easier than that, although it is equivalent to a notch filter. It is the time domain version of a notch filter, which is a signal averager that averages over exactly one 60 hertz cycle. So you take 10 measurements equally spaced over the 60 hertz cycle, average them together, the noise cancels out.
I mean, if you go to some other country where they've got 50 hertz signals,
Throw away your digital multimeter, get a new one. Although it's possible to have the system detect that and do it automatically. So, if you want to get obsessive, you can do the signal averaging. I don't think you'll need it for the accuracy I'm asking for.
And so if you're trying to measure a 60 hertz signal with the multimeter, then it can't do it?
Well, then you take it out of DC mode and put it in AC mode. I'm not asking you to generate an AC mode here. How would you make an AC multimeter? Ooh. Yeah. Well, what do you mean by an AC multimeter? Do you really mean that it reads the peak, the average, the root mean square, the minimum? That'd be boring. What? All right, so how would you do root mean square? Yeah, you could heat a resistor. That would be a very accurate way of doing it, but very slow, by measuring the power directly by heating. Well, we'll worry about that later. Any questions now about Lab 2? Yes?
Yeah, so when you draw the diagram, is there any specific reason you draw like
There's always a specific reason.
picking B2, connected to the probe before that like two diodes and then per limiting resistance?
Because if you've low pass filtered it here and you're measuring frequency,
But
it depends on whether your frequency is within bandwidth of this capacitor or not. It would be safer to hook it on here, but if you make this capacitor rather large, you'll filter out the frequencies of interest. And I don't know the answer whether it's all self-consistent or not.
but then we'll take the risk of like
Blowing out that
blowing
input.
out
Absolutely. You could do a two-stage thing where you have 1K diodes, another 1K like that, and then hook on right there. That would be very safe. You got to think noise, folks. It's analog. It's ugly. You got to think noise. You're going to have to scope everything. You're going to have to play with the power leads. You're going to have to worry about noise on the power. You think of power leads as being clean, but they're not. And the reason is that the current fluctuations in the CPU are enormous, on the order of gigaamps per second. 10 to the 9th amps per second. Not a very big current, but it changes really fast. Gigaamps per second, let's see, resistance, the voltage drop across an inductor is L di dt, right? Any piece of wire is an inductor, including the 4 inches of wire from the power supply to your CPU. The few nanohenries of that wire multiplied by a few giga amps per second can result in volts of voltage drop due to the power supply leads. That is in fact why there are capacitors coupled as close as possible to the CPU between VCC and ground to short out that inductance. It doesn't get it all, though. Any other questions? It's a simple circuit you're building. I guarantee you will see all manner of weirdness. Let's go back to digital side. A to D converter. Likes to run between 50 and 200 kilohertz. We need to set it up with a prescaler. We need to be able to turn on and off the conversion. We need to be able to set what channel we're recording from. By the way, another way to do all this stuff is to just record different channels for different gains. But for now, let's just say we're going to record from channel 0. And so we need to learn how to set the register AD mux, which does a bunch of this function. In fact, there are 5, 1, 2, 0, 1, 2, 3, 4. There are 5 bits of mux. 32 possible inputs from 7 pins. 0 through 7 are the single-ended channels for pin 0 through 7. But other combinations set the A to D converter into differential mode for different pairs of pins. And 11110 is the internal reference. And 11111 is ground. The top 2 bits set the value of Vref. Remember that Vref is the maximum voltage that you can convert. It is the voltage to which the input voltage is compared. Vref can be set to 0, 0, which is external, 0, 1, which is AVCC. That's pin, what pin is that? From homework 1? AVCC is which pin? 30 or 31 or 32? I can't remember which. 30. Thank you. AVCC 11 is the internal 2.56, and I'm going to quote this because this is plus or minus 0.2. And 10 is, quote, 1.1, quote. If you choose external, which is the default, then you must mount the Vref jumper on the STK500. If you choose any of these, you must unmount it. No choice. This bit is referred to as the ADLAR bit. That's the analog data left adjust register. Love it. That's obscure. What in the world does that do? Well, we have two 8-bit registers, which are the ADC high and ADC low, each being 8 bits. If the ADLAR equals 0, ADLAR equals 0, then the data is presented with the 2 high order bits here and the 8 low order bits here. If the ADLAR is equal to 1, then the registers are set up high and low so that the high order 8 bits are here and the low order 2 bits are here. You look pained. Why are you looking so pained? Yeah, so is that different than the rest of the microcontroller? So, yes, it is confusing, but the reason for it is that if you want to do just an 8-bit conversion, which you often want to do, and which, for instance, for this lab is good enough, then you set the ADLAR to 1 and read the high register. You don't even have to bother reading the low register. However, if you do read the low register, because you set the ADLAR to 0, if you do read the low register, you must read the high register or the AD converter is locked out forever. If you read the low register, you must then read the high register afterwards. Otherwise, the AD converter is locked out indefinitely until you read the high register. So, either set the LAR to 1 and read the high register, or set the LAR to 0, read the low register, then the high register, and then concatenate them with the appropriate arithmetic.
Why can't they just have it so that ADLAR is always set to 1 so that you can read, if you just want an 8-bit conversion, you read high, and if you want all 16, you read...
I can't answer that. That's a religious question. Why did they decide to make the default this instead of that, or that instead of this?
Why even have an option?
Why have an option? I don't know. But that's, Arnie and Vern decided to do that, right? So... Okay, so in addition to the data registers and the AD MUX, there is an analog digital converter status register A, which implies there's probably also a B register, and there is. And this register has all manner of useful stuff in it. One is ADEN. That's the analog converter enable bit. This has to be set to 1 if you want to do a conversion. This bit is AD start. It's called ADSC, and if you hit the ADSC with a 1, a conversion is started for you. So if you set this value to 1, it starts a conversion, and it's auto set back to 0 when done. So you can set this bit to 1 and start polling it to see if it's 0, and as soon as it's 0, the conversion is done. Or you can turn on an interrupt flag. This is the ADIF interrupt flag. Actually, that you don't want to mess with that. You want to turn on the AD interrupt enable bit. If you turn on the AD interrupt enable bit, you better write an interrupt service routine to handle what happens when the conversion finishes. ADIF. This bit is the A date, and I don't want to talk about it much except it allows one of 8 different randomly selected events to trigger the A to D converter when coupled with the other register, the B register. I just don't want to talk about that right now.
So, Professor,
Yes?
when one conversion is done, it will set a ADIF, right?
If you have set the interrupt enable, then it will set the ADIF when the conversion is finished. Otherwise, it will not set it.
Okay. So I enable it, it will just trigger and interrupt when conversion is done.
If you set the enable bit, then the interrupt flag will be set when the conversion is done, and it will trigger an interrupt. And you better have written an interrupt service routine for that. Otherwise, it will go into the ozone. It would blue screen if it could. This is the prescaler. We want to set the prescaler to 111, probably. Corresponds to a divide by 128. 16 times 10 to the 6th hertz divided by 128 is 125 kilohertz, something like that. That's halfway logarithmically between 50 kilohertz and 250 kilohertz, and so that's a good division factor. So we're almost always going to set these to 111. Yes. It takes about, it's 13 to 14 of these cycles, 125 kilohertz cycles, to do a conversion, suggesting that it takes around 100 microseconds to do a conversion.
Why would you why would you want that just going falls out and not set the prescaler? Why do we reduce the speed?
Oh, we reduce the speed because the bandwidth of the analog circuitry is not fast enough to go megahertz. The bandwidth of the analog circuitry is not much above 250 kilohertz. So if you set this to, if you set the prescaler to 1, you'll get a conversion in one cycle, machine cycle, and it will have 1 bit of accuracy. Oh, well, in that case, why don't we just use the digital input? So,
Is there a limit on that prescaler? Are you not allowed to set it? Or could you screw it up and set it?
oh, you can totally shoot yourself in the foot.
Is that explained in the data sheet? The analog?
Yeah, if you can figure it out. Right, that's the worst piece of the data sheet I've seen is the analog section. But you can set it to divide by 64 and it'll still work. It'll degrade slightly. You'll still get 8-bit accuracy. It'll be twice as fast. For this, you don't care. Because you're only going to take about 5 readings a second. That's as fast as a human can read.
Yes, sir.
So it takes a couple hundred milliseconds to update the LCD. How fast does a digital multimeter in the lab actually take a reading? Has anybody been annoyed by how slow they are? I have. It's about 1.2 seconds. It seems like forever. It's not fast enough. In fact, Apple, of course, has a guideline for what constitutes simultaneous in the eyes of the user. In other words, you click, it happens, and it's considered fast enough. Does anybody happen to know that number? About 200 milliseconds, 200 to 300 milliseconds, which just happens to be the length of time it takes for your brain to process an event to consciousness. You say, wait a minute. How can it take 200 or 300 milliseconds to process an event to consciousness when you can press a button less than 200 milliseconds after you hear it? It's not conscious. You think it is. It actually happens before the awareness of it. But you backdate the awareness because it's time-stamped. I'm not making this up, folks. It's time-stamped. The event is time-stamped in your brain to refer to the past. And so you perceive it in the past. If you change channels, if you mess with the mux, if you change the mux at all, you double the conversion time to 25 to 30 cycles. Because it has to do an auto-calibrate every time you change the mux. So, if you're reading channel 0, channel 1, channel 0, channel 1, then you will automatically take a factor of 2 hit in the conversion speed. Again, for this lab, it hardly matters because you can leave it locked in on channel 0.
ADC sleep mode, do you use the same interrupt as the one ISR as the one you set when you enable ADIE?
So ADC sleep mode. Excuse me. ADC sleep mode is the entry into ADC sleep is controlled by the sleep mode register, which is something like GW, the general interrupt working register, GIWR, something. It's in the first few pages of the manual. You set the sleep mode to ADC sleep. You enable sleep. You start a conversion, and then you use the assembly keyword sleep. The CPU turns off. It's dead. And nothing will ever happen again unless you have set an AD conversion and turned on the AD interrupt. In which case, when the analog conversion finishes, it'll trigger an interrupt, wake up the CPU. If you didn't set the interrupt enable and start a conversion, it sits there forever. Does nothing again. So you can use that to cut down noise. It gives you another bit or two of dynamic range. But you don't have to use that for this lab. But it's good practice if you want to. What other questions? We're going to debug with oscilloscopes in this lab. High-level debugging with oscilloscopes. So is anybody intrigued by the idea of a smart wastebasket? Apparently, smart wastebaskets are being deployed in London for the Olympics next year, including LCD panels on the front. Man, how long do you think those things are going to last? You get out of a soccer stadium. Never mind. I'm not going there. What?
We'll steal them for their projects.
It's a great idea. I mean, clearly it would be nice to give people some feedback. Experience shows that if you give people feedback on their behavior, they modify their behavior. My dad, who is a lead-footed guy, always drove his cars, you know, just stomp on the V8, go as fast as you can, hit the brakes as fast as you can, until he bought a Prius. And the Prius gives him feedback on mileage. And now he's become a mileage geek. I got it about 51 for the last tank. And it's completely changed his personality and behavior. He's now the mellowest driver you ever saw, creeping down the damn road. And it's the feedback. It's the instantaneous miles per gallon meter changed him.
Fundamentally different.
Fundamentally different.